Alright, so welcome back. Today we're talking about Boyle and Charles' law, and honestly these are just a study in proportion, so it goes pretty smoothly. These are our first two gas laws, and they're kind of the more common sense ones. So with that in mind, let's kind of introduce our characters today. And our first character is this guy by the name of Robert Boyle. And you'll notice that Robert Boyle lived a long time ago, in the 1600s, and he's an alchemist, right? Someone trying to turn lead into gold, or however you want to talk it, find the elixir of life. But he also had something else going on. See, Robert Boyle was really the first chemist, the first person to do science. You know, if you look at this timeline, and you think, oh, well, Robert Boyle, he's an Irishman, you figure out that he's a contemporary of Francis Bacon, who we can talk about as like the first person to do scientific method. And while Boyle wasn't necessarily a student of Bacon's, the kind of thinking was concurrent. And Boyle deserves a lot of credit for starting the field that you're studying right now. And he did so by studying gases, so it shouldn't come as too big of a surprise that we're studying gases as part of chemistry. And let me be clear, Boyle did real chemistry. Let's take a look at a picture of his experiment here really quickly. Again, I want you to think about this. This is a long time before the founding of the United States. This is at the very beginning of the scientific method, and we're talking about quite elaborate apparatus. And I don't want to go into the details of the experiment too much, although it was relatively easy. For the time, it wasn't. And the amount of thought and the amount of learning that came from this apparatus is really quite notable. And the key thing we learned is this. We call it Boyle's law. That at a constant temperature, the volume and pressure are inversely proportional. So a quick question. I want to bring out that for a little bit more. The fact that temperature doesn't change is going to help us know this is Boyle's law. So every single law we cover, at least at the beginning, is going to have a constant in it. Now, Boyle did this, and while graphing wasn't really a thing when he did it, we could graph volume versus pressure, and we would get a shape like this. So another question. And I want you to notice, effectively, that this curve isn't linear, right? It's not a straight line. And I've chosen 3 points on the line, and let's take a look at those for just a moment together. All right, so I have this drawing here of each of the 3 situations where I have 1 atmosphere, 2 atmospheres, and 4 atmospheres of pressure, and these 3 volumes. Let's start up here. 1 atmosphere, 10 liters. So at 1 times 10, I get 10. Now I take this piston, I push it down until it's half the size it was before, and all the molecules in here get squeezed into half the space. Okay, that makes some sense. And when I do that, the pressure rises by a factor of 2, right? If my pressure went up by 2, that means the volume had to go down by 2, right? If this got half as big, the pressure got twice as large. And I can see that if I take the 2 atmospheres times the 5 liters, I get my 10 again. Okay, when I take that piston, I shove it down even more, right? I was at 5, so let's go down another half to 2.5. And I measure the pressure, and I find it's 4. Well, 4 times 2.5 is 10. And that the fact that these things are coming out as a constant tells us something. It tells us that these molecules within this cylinder are responsible for the pressure, and as long as we keep this temperature constant, the only 2 things that are related to each other are the pressure and the volume. It's a really brilliant and elegantly simple thing. We'll come and we'll take a bigger look at Boyle's law in just a moment. But I want you to see this like as one value goes down, the other value goes up, this inverse proportion. Now let's take a look at another guy really fast. Let's go forward like, I don't know, 200 years in history, a very long time, to a man named Jacques Charles, who was an aeronaut, which is a favorite word of mine. Jacques Charles is a character, and I can't give a lecture on Charles and Boyle's laws without talking about Jacques Charles for a moment. First off, let's take a look at this guy's picture. Pretty fly-looking dude. Kind of directly. See, he was an aeronaut. An aeronaut was the name for the first human beings to ever fly. And Jacques Charles did fly. Actually, he flew the second human on Earth, just behind the Montgolfier brothers. 10 days behind, not close. And they were very different flights, I should point out. Both launched near Versailles, but the Montgolfier brothers used a hot air balloon. And Jacques Charles used hydrogen. So you have in the, right around 1800s, a balloon full of an explosive, lighter than air gas, and some guy, actually not only Jacques Charles, he had a friend, the Robert brothers, who were also on it, that got on board and got lofted up by this giant balloon full of hydrogen. Now, if you read what Jacques Charles was doing, you will find that he actually was inspired by Boyle's law and Boyle's work. He had access to them. He was wealthy and lived in the aristocracy of France. And he thought that hydrogen might be a suitable lifting gas for a dirigible, for a balloon. And he was right. Now, they didn't just build a balloon and launch it and say, well, I hope we float. They did a test before. And that test ended in its own kind of unique way. See, the balloon was unmanned. And the balloon went like 45 miles away from where it was launched. And they tried to keep up with it on horseback. Well, the balloon landed in a village. And of course, your peasants and farmers don't know what a balloon is. No one knows what a balloon is except for the French aristocracy. And literally no one on humankind had ever built one of these things before. And this thing comes falling out of the sky with no explanation of where it came from or whoever made it. And so they attacked it with pitchforks and knives and yeah. That happened not that long before Jacques Charles got in the balloon. Actually, the French aristocracy said, well, you should put criminals in the balloon, not Jacques Charles. We can't afford to lose you. But Jacques Charles and his friend, the Robert brothers, were aghast at such a recommendation that they wouldn't be the first to fly. And they ended up not being the first to fly. They were beaten to the punch by, again, 10 days just because a hot air balloon. But the reason why they were flying the balloons wasn't just to be dope. Don't get me wrong. Part of this was just pushing boundaries. But they also were interested in studying the atmosphere above the ground. And one thing Jacques Charles would do is he would collect jars of air from aloft. And one of the things he was trying to do was study Boyle's law more. And as he was doing these things, studying these things in his lab and taking the flights, he came up with something known as Charles' law. Charles' law says that at a constant pressure, temperature and volume are directly proportional. So, constant pressure. Remember, Boyle's law, constant temperature. Charles' law, constant pressure. And we have a difference here because we no longer are looking at an inverse proportion with its curvy graph. We're looking at a direct proportion with a straight line. As the temperature doubles, the volume doubles. That's simple. Again, if this is a constant pressure. Let's ask a quick question. Which one of these graphs, A or B, shows an inverse proportion? Another question. Which one of these graphs, A or B, could possibly show Charles' law? So I want to come back to here for a moment because I noticed something weird. My temperatures are in units of K, which maybe you've come across, hopefully you've come across, you should have come across, but maybe you haven't. Those units are Kelvin. In this class, temperatures are always in Kelvin. From here on out, this chapter, if you're dealing with the temperature, it's in Kelvin, period. If you don't have Kelvin, you have to convert to Kelvin. Now, the formula for converting to Kelvin is very easy. You take the temperature in Celsius and add 273. That's it. If you type it into Google, you will get more digits, at 0.15 specifically. For your homework online, I am going to assume this 273, and that's it. A quick question again. What unit must temperature be in? Another thing that will come up, degrees Kelvin doesn't actually exist. The unit is K. If you write degrees Kelvin, you're not wrong. You just sound stupid. Think about it as saying like scoring a goal in football, but not like actual football, like American football. We understand what you're talking about, but it's not right. Okay? Don't write degrees Kelvin. It's just Kelvin. So let's do a couple quick practice problems just in case we need to. How many Kelvin are in 20 degrees C? Well, I would say that K equals 20 plus 273, right? The degrees in centigrade plus 273. So I would have 293 Kelvin. And again, don't write degrees K, right? It's 293 Kelvin. Let's have you do one. How many Kelvin are in negative 30 degrees? So you should get 243 Kelvin. So again, if you come across a temperature, it will generally be in centigrade or Celsius, and you need to convert it to Kelvin. And this is going to be a common mistake for people in this class, that you forget to convert to Kelvin in a gas laws problem. It has to be in Kelvin, period. If you don't have a sheet of paper out, I really suggest grabbing one now, writing down the conversion formula, and then getting ready to make a chart. Let me get this cleaned up. All right, so it's my suggestion that you set up something like this, kind of an area to compare Boyle's law and Charles' law. And the first thing we need to do is write down the mathematical formulas for both things. So let me get those down and then explain them to you. All right, so you'll want to write these down. First off, question to help you pause. Which of the following is Boyle's law? All right, so we've got these subscripts, 1s and 2s, and these mean like before and after, right? 1, let's say, is starting, and 2, let's say, is ending. So P2 is the pressure at the end, and V2 is the volume at the end. V1 is the volume at the start, and T2 is the temperature at the end. You might notice that I've written Boyle's law in one way, and Charles' law I've written as two different possibilities, right? I think most students find it easier to work with this equation, but easier to memorize this one. Now, obviously memorization is not a big deal for you because you'll have your notes in front of you, but we have this starting and ending thing. Let's get another note down. Right, so Boyle's law is inversely proportional, and Charles' law is directly proportional. So those two things kind of help us know which equation's which. Again, I'm hitting these points home only insofar as these proportions make the math easier, because you've dealt with proportions a little bit in algebra. Finally, and this is going to matter more to us in a moment, Boyle's law happens at a constant temperature, and Charles' law happens at a constant pressure. So here we are. Before we move on, a couple quick questions. All right, so let's move on. The next thing we need to do is decide, do we use Boyle's law or Charles' law? And how do we know how to do that? So let's clean this up and get some new examples up in here. All right, so let's learn how to deal with a question. Now, the hardest part of this chapter for most people is that the questions are going to be word problems, always. So let's go through it and understand how to do this. The first thing I do is anytime I find a number and a unit, I'm going to go ahead and just circle the number and the unit. Not even reading the questions. I'm just looking for numbers and units. Great. Got my numbers and my units circled. And what I'm going to go back is I'm going to start labeling these numbers. Liters. Liters is a volume. Meters, I don't use meters. Meters aren't useful to me. They're not a volume, pressure, or temperature. And being clear, if it's not a volume, temperature, or pressure, we don't use it. And both these things have units of ATM. So what are those? ATMs. All right, so now that I've done that, I can actually read the question. A diver blows a 0.75 liter air bubble. As it rises to the surface, the pressure goes from 2.25 atmospheres and ends at 1.05 atmospheres. What would the volume of the air bubble be, assuming the temperature stays constant? So the first question I am going to ask is what is not changing? Well, what's not changing, what is constant in this problem, is the temperature. And that is the trick. If I know that I'm using constant temperature, I'm going to use Boyle's law. And the reason why I'm using Boyle's law is that it's got a constant temperature. The other way you can think of it is nowhere in here is temperature mentioned at all in terms of number. And Charles' law needs not one but two temperatures. So there's no way I could solve this equation. I have to use the equation that uses P's and V's. I have a diver who blows a bubble that's 3/4 of a liter underwater. And when he's underwater, which pressure is true? Which pressure is the diver experiencing? This one or this one? Okay, because the pressure is higher under the water than near the surface of the water, right? So this bubble is going to rise, just logically, it's going to get bigger, right? Bubbles get bigger as they rise, until it reaches the surface of the water, which is at 1.03 atmosphere. So we know what's going on, and from here we know that these two things are happening at once, and this volume is what we're looking for, right? Mathematically, P1, V1, P2, V2. Let's say this is our starting condition down here below the line, and these are our ending conditions. These are our 1 conditions, these are our 2 conditions. Well, mathematically, that's 0.75 and 2.25 equal to 1.03x. Now, right off the bat, a couple of you are going to be like, Mr. Knight, you put the volume first and then the pressure. Okay, it's fine. Right? These are their multiplication. The order doesn't really matter. Okay. So these two things together, this thing with an x, this looks a lot like an algebra problem. All right, so I multiply these two things together, and then I need to get x by itself, so I need to divide by the number out front. And I get 1.638. I've got 2 sig figs as my lowest, so 1.6. And this is a volume, and it's going to have the same units as the other volume. So since this is in liters, this has to be in liters. All right. A little tricky the first time. A little bit of algebra. That being said, the thing that's most likely to mess people up is picking out which things are P1, V1, P2, V2. Let's take a little quick breath, and then let's move on and take a look at another question. All right, 33 liters. Is that a volume, temperature, or pressure? 300 K, is that a volume, temperature, or pressure? Okay, so now let's go ahead and look down here. I've got another temperature, Celsius. All right, a balloon has a volume of 33 liters and a temperature of 300 K. What volume? Ooh, here's a question. This says volume, right? Will the gas occupy at 38 C, assuming pressure remains constant? Okay, so what's not changing is pressure. And right off the bat, that means I can go back over to my notes and I can say, ooh, a constant pressure, this has got to be a Charles' law problem. Or, if I wanted to, I could look and say, hold on, let me write this out. V1, T2, V2, T1, hey, I see TV, TV. Well, TV, TV. There's no way I could use Boyle's law. There's no pressures mentioned anywhere in the problem, right? So I have to use the equation that I have the variables for. Now, I think for most students, this form of the equation works more easily because there's no cross multiplication. So I'm going to use this to teach, although personally, I use this because, I don't know, proportions look easier that way. All right, so V1 T2 equal V2 T1. So the question is, really, once I have this is the hardest part of the problem, is picking the equation, in my opinion. Once I have this, I need to come up here, and I need to figure out which one of these things are 1s and 2s. Okay, so these two things are linked, right? It has this volume and this temperature. What volume at this temperature? So it doesn't really matter which one we call 1 and 2 because, multiplication. But let's call these kind of the starting things, right? So these would be V1, T1. What volume will occupy at this? Okay, so these would be T1, T2. Cool. So I go to plug my equation in. V1, 33 liters. Easy. T2, 38C negative. Can I use that temperature? Ah, right, because it's got to be in Kelvin. So we need to do a quick Kelvin conversion. So I get 235 Kelvin. If you don't use Kelvin, you will get this question wrong. Use Kelvin. V2 is our x because it doesn't have a number, and T1 is 300. Great. Looks like an algebra problem to me. Multiply these two things up, divide by 300, solve for x. All right, so I just noticed that I didn't put a decimal here, so that would technically throw off your sig figs quite a bit, right, because you'd have to round this to 30. So I have two numbers here with 2 sig figs, so my answer here needs to be 2 figs. So I'm going to get 26 liters. Again, I care much more about the algebra and picking the equation than getting the right number of sig figs. Let's do a sanity check. A good thing to do before you go on is make sure, hey, does this answer actually make sense? Well, the balloon was warm and it got colder, and as things that are warm get colder, they shrink. So yeah, the balloon got from here to here. It got smaller. This checks out. I thought about doing another example, but this video already feels pretty long. And so what I'm going to do is I'm going to embed a video into your homework that you can use to check. So if you're like, these two examples, that's plenty for me. I don't need to go on. Perfect. And if you're like, I could really use one more example. Well, at the top of the homework tomorrow, there'll be a video going through this question here. I'm planning on giving you like 6 of these to do tomorrow, and I'll break them out into pieces. So for now, there's nothing else you need to do. I hope you have a great day. Be gentle to each other. Y buen camino en todo.